Okay, let's start. Welcome to our VAPS seminar in December. It's our honor to introduce Jiajun Zhang from Auburn. He's going to talk about conversion of free boundaries in the incompressible limit of tumor growth. Please, Paul.
Thank you so much, and many thanks to Professor Hang for the invitation. I'm really honored to come to the VAPS seminar to share with you my ongoing project with Jiajun Tong. Jiajun is from Peking International Center of Math Research, and the work is about the convergence of free boundaries in the incompressible limit of tumor growth. It is still an ongoing work, and hopefully we are going to post the paper to archive. And of course, it's my first time to talk about this topic. And please bear with me if it is not so fluent, if my talk is not so fluent. Anyway. We study tumor growth models, and there are two types of modeling, so two types of viewpoints. The first one is we try to describe tumor cells as an evolving distribution in space, and then we might need to use some parabolic type equations to describe the involvement of the distribution. Or alternatively, there is another viewpoint, that is, we try to describe the region where the tumor cells reside, and we try to figure out the dynamic of how the domain is evolving. And this is a more geometric description. So you can have a look at the figure here. So omega t denotes the region where we have tumor cells, and then the key point is to describe the capital V, the velocity of the boundary of the region. It turns out to be very interesting that these two different viewpoints are linked by the so-called incompressible limit. To discuss the detail of the incompressible limit, let me describe the two equations. The first one is the Porous Medium type equation, and it lies inside the first viewpoints of describing tumor cells. So rho is the involving density of the tumor cells, and P here denotes the pressure. And the pressure is equal to, so in this model, pressure is equal to the density to some power m, m minus 1. And m is a parameter. And B here is the drift term. It is a given function of space and time, denoting some background trait of the how the background we want to push the tumor cells to move, so background velocity field, and F tells us the growth of the tumor cells. Another model is the Hausdorff type equation. So here, the region where P is positive is the region where we have tumor cells. And how we describe the movement of the region is by solving an elliptic equation in the region. So you solve for P in the region, and in the region where P is positive. So you solve for P first, and then the region is evolving with respect to some velocity, and the velocity is a velocity field given by the solution P. So of course, it is a free boundary problem. Among the models, rho is the density and P denotes the pressure. So far, so good. If you have any comments or questions, please feel free to interrupt me. And let me talk a little bit more about the porous medium equation. If you use the relation between the pressure and the density and plug in it into the equation, you get this porous medium type equation. So we have degenerate diffusion because m is greater than 1. And it is often very useful to study the pressure variable. So we also look at the equation that is satisfied by the pressure. So Pm is the pressure, and it solves a different parabolic type equation. One key feature of the porous medium type equation is the finite propagation property. That is, if initially the support of the solution is compactly supported, then it remains so for all finite time. That is to say, the region where we have tumor cells will propagate with a finite speed. And then you can describe the boundary of the set. It is called the free boundary. So you can see that both models feature free boundaries. And now I can describe the incompressible limit. That is, we pass the parameter m to infinity. And it can be proved under some conditions that both the density variable rho and the pressure Pm, they converge strongly in L1 spacetime. And you can expect that the limiting pressure is the solution to the Hausdorff type model. So first, let us try to roughly take a look at what we expect as the limit. So here I plot this graph of rho to the power m minus 1. So you can see that as m goes to infinity, whenever the density is less than 1, you expect the pressure to be 0. And if rho cannot be greater than 1, because at the limit, rho infinity cannot be greater than 1, because if you look at the equation, when m is very large and rho is greater than 1, the diffusive effect is super large. So it will diffusive immediately. So rho is always less than 1, and whenever it is less or equal than 1, and whenever it is strictly less than 1, the pressure is 0. So we have this graph relation. And also, when m is super large, if you look at the pressure equation, when m is super large, you expect that the middle term is 0. And this is the so-called complementary relation. And so what we have is, we have some regions where we have rho being 1, and in those regions, you can solve for p via the elliptic equation, and then you make this middle guy to be 0, and you have the remaining equation for p, and that equation will give you the motion of the region. So how the region is evolving, you can obtain that by solving the equation after hiding the middle term. And in the region inside the region where rho is 1, you can solve for p by the complementary relation. So this is what we might want to expect as a limit, and that is why we get the limit as the Hausdorff flow. And now let me tell you the literatures about the incompressible limit. So it dates back to 1987. I think the first paper about this is by Caffarelli and Friedman, and they considered the porous medium type equation. And later, Benilla, Baccardo, and Hirori also studied the problem. For the porous medium type equation, the limit as m goes to infinity is stationary. That is, as m goes to infinity, we have the limit is a function of x only. While when you add the growth term, the limit becomes dynamic. So we have a lot of literatures for the problem. Pathan, Kuros, Vankis, Kim Poser, David Schmidtchen, Kim Millard, Golem, Kim and Millard, they studied the problem. And let me mention that David Schmidtchen, they proved the complementary relation. And Golem, Kim and Millard, they concern the case when G is a function of x and t, and they allow G to be both positive and negative. So they lose some monotonicity. And you can also add a drift term. So you can also add this drift to the equation. And there are also a lot of literatures on this. The first paper I can find is by Alexandro and Kim and Yao in 2014. And later we have results by Craig Kim and Yao, Kim, Posa, Woodhouse, David, Debix, Perthan, and Raymond Chu. So let me mention that this paper done by David and Debix, Perthan, they studied the rate of the convergence as m goes to infinity. And Chu studied a more general problem where they have a variable upper bound on the density variable. And it is also interesting to take consideration of nutrients. That is to say, we have growth term as a function of the pressure and C. And C satisfies some parabolic type equation. So you have a system here. But then Kuros, Vankis, and David Pathan, they studied the problem, the convergence for the tumor growth with nutrient. And finally, let me also mention that the incompressible limit also appears in fluid equations. For example, we have this Navier-Stokes model, and people studied the incompressible limit for the Navier-Stokes model. Okay, so we have a bunch of literatures about the incompressible limit, and most of them are about convergence in L1, in space-time L1. And since we know that the two equations are featured by the free boundaries, so a natural question to ask is, do we have convergence of free boundaries? And for this problem, we are not able to find out many literatures. It is probably due to some difficulties that can be seen directly. So, for example, we have lack of the regularity of free boundaries, because when you have the drift term, the velocity field can push the free boundary in different directions, and it is possible that two free boundaries can be pushed together at some time, at some large time, maybe something like this. So two parts of the free boundary, they can be pushed together at some time, and when the two parts of the free boundary attaches, then there are topological changes, and there is some singularity that can be developed. And also there is a lack of uniform regularity of the solutions. For porous medium type equations, the pressure variable is often can be proved to be a Holder continuous, while it is not clear that we have uniform regularity in M. And for the density variable, actually there is no uniform regularity, because, for example, if the initial pressure is non-degenerate, then the initial density variable becomes like a characteristic function, because the density variable is equal to a constant is like the initial pressure to the power 1 over n minus 1. So if the pressure is in some is not too small near the free boundary, then the limiting density is more or less like a characteristic function, and the limiting density is a patch solution. So it will be a characteristic function of space and time, and then we don't have we don't have any continuity of the density variables. Before telling you our approach to go over the difficulties, let me first share with you our results. So together with Jiajun, we try to show the convergence of free boundaries, and we need the drift term to be C2 in X, C1 in time, and we need the growth term F to be C1, and we need some monotonicity. So divergence of B plus F minus partial F partial P times P to be strictly positive. And then if the pressure variables forms a Cauchy sequence in L1, in spacetime L1, and the support of the pressure expands strictly relatively to with respect to streamlines at time 0, uniform in M. So under these conditions, then the free boundaries converge in Hausdorff distance for positive times. So when the time is positive, for all positive times, the free boundaries are very close when M is super large in Hausdorff distance. The condition that PM forms a Cauchy sequence is easy because it is verified by the literature. We have convergence of solutions in the incompressible limit. For the second part, we need some initial uniform expanding of the pressure, and it turns out to be interesting here actually, but I will tell you more details. But more or less, this is about initial data. So if the initial data is nice, then the initial support will expand uniformly in M. And after that, we want to study the Hausdorff dimension of the free boundary. This is because this is motivated by by the following. So we know the free boundaries are close in Hausdorff distance, but if the free boundary behaves really weird, so something like this, okay, then the red guy is also close to it in Hausdorff distance. So we don't want this to happen, and so we want to ask, okay, well, can we show that the free boundary is nice? And this is what we can get. So this is a hard problem, and what we can get is under some extra conditions, and we need the initial data to be a characteristic function of some set, and actually, we allow the initial data to be slightly more general, but more or less, we need it to be a characteristic function of some set, and then we can say that the free boundary of the Porous medium type equation, it is of Hausdorff dimension d-1 plus a constant over m-1. So when m is super large, then the Hausdorff dimension of the Porous medium type equation is close to the Hausdorff dimension is close to d-1, and after passing m to infinity, we can show that the limiting free boundary has finite d-1 Hausdorff measure. But we believe that the free boundary for the Porous medium type equation is nice, but this is all we can get. And there are some literatures about the limiting solution as well. For example, Pathem, Kuro-Venkis, and the Millet, Pathem, and Kuros, they studied the patch solutions to the Hello shell flow with source, so the limiting problem. And they can show that the free boundaries have a finite parameter, and then they also, and then Millet, Pathem, and Kuros proved finite d-1 Hausdorff measure. And when there is both source and drift, Kim, Poser, and Woodhouse, they also studied the problem, and their results amount to space-time finite parameter of the free boundary. Okay, so now let us go to the proof part. And any comments or questions? Okay, so let me try to discuss the proof. The first thing we need to do is we want to generalize the Arrowson-Bernina estimate, and this is one place we need B and F to be regular, and the estimate is essentially about the lower bound of Laplacian P. And what's nice here is as m goes to infinity, you can see that the right-hand side goes to 0. And C0 is independent of m. And then we will use, so the technique we will use is, or the idea we will use is the we call it L1 estimates imply propagation properties. And what does this say is, the philosophy here is, if the pressure has a large average near the free boundary, then it will push the free boundary to expand fast. And if the average of the pressure is small near the free boundary, then it will hinder the rapid movement. This is a highly non-trivial statement, because it amounts to like L1 estimates imply some point-wise information of the free boundary. And that is why it is non-trivial. And this is done firstly by Caffarelli and Friedman in 1980s for the porous medium type equator. And another nice thing about this is we don't need any regularity of the free boundary, and we can tell the point-wise information of the free boundary by L1 estimates. So that's a nice part. However, we need some uniform estimates in M. So unlike Caffarelli and Friedman, we need uniform estimates in M. And another thing is, because of the drift term, the free boundary is automatically moved along the drift. And so our expansion, by which the expansion we mean is the expansion relatively to streamlines. And by streamlines, we mean the integral curve of the vector field B. So if the free boundary is moved along the streamline, then we say that there is no expansion. And there's no expansion of the free boundary. Okay. Okay. And here I'm writing down the two lemmas. So the first one is about a small average of the pressure. So if the pressure is is 0 in a ball at time t0, and it is small in the future. So here is the average of P in some ball with another center. So recenter the ball along the streamline, and then you look at the average. If the average is small, then Px at time t0 plus tau is 0 near the center of the new ball. And this says that the free boundary cannot move too fast. And on the other hand, if the average of the pressure is large, then in the future, the pressure will propagate to the center of the ball. So large average of the pressure implies a fast movement. And our contribution here is, the first one is not too hard. We extend the two lemmas to general equations. And the second one is we obtain uniform estimates in M. So all the constants here, C0, C1, C2, and the lambda, they are independent of M. And for this purpose, we need new barriers in the proof. And now I can tell you how the two lemmas and another ingredient that will come in a moment, the so-called weak non-degeneracy, they will imply the convergence of the free boundary. So let us take a look at this free boundary. So we take Pm and we fix one time T0, and we have a free boundary. And then let us circle a ball here. So a ball centered at a free boundary. And let us assume that we have some weak non-degeneracy. That is, the average of the pressure is not too small. By not too small, I mean the pressure has a less than quadratic growth near the free boundary. So R is the radius of this ball. And if this happens, then because PL and PM are close in L1, so we know that the average of PL is also large in this ball. And then by the lemma, we get that at some future time, so T0 plus tau, the support of PL will propagate to cover the center of the ball. And then one can also show that the free boundary of PL at time T0 and T0 plus tau needs to be close. In that way, we can tell that the distance, the Hausdorff distance between PM and PL cannot be too large. So that's the idea of the proof. And of course, here you can see the key points are the two lemmas and the weak non-degeneracy. So we need this. And another thing you might notice is here I used L1 convergence in space. However, this is a problem that can be solved easily because there are some more tonicity. Now one can show that if PM is large in a ball at one time, then it will be large in some ball, okay, in some ball for a short time. So that is not a problem. So convergence in L1 or convergence in L1 in space or convergence in L1 in space and time, that is a technical issue that can be overcome easily. However, we need this weak non-degeneracy. And this weak non-degeneracy is the same as a strict expansion. So the lemma tells us that if you have weak non-degeneracy, that is the same as the average of the pressure is not too small near the free boundary. And this largeness will force the free boundary to expand strictly, relatively with respect to streamlines. So this is the same as strict expansion of the support. And so we need to show that if the initial free boundary is expanding strictly relatively with respect to streamlines, then such expansion is propagating to all time. So we need to propagate the strict expansion of the support to all finite time. So that's what we want to do. And this is done actually by Kafrad and Friedman in 1980s by a compactness argument. So it's nice. This has been observed before, but the argument they used cannot be applied here because via a compactness argument, their constants depend on m, and we need uniform estimates. So we cannot apply their argument. So here is what we do. The first thing is we need some condition to guarantee initial strict propagation. And it turns out that this is a little bit interesting because for the Porous Medium Equation, in the literature, we know that if the initial pressure is non-degenerate, then the free boundary will expand strictly. There will be no waiting time. However, since we need uniform estimates, it turns out that this condition alone is not enough. This is because if you look at PM, so PM, if the support of PM is a cone somewhere in the somewhere, and such PM can be non-degenerate. However, if you pass M to infinity, the limiting pressure is solving an elliptic equation in this region. Okay, and in that case, we know that if by some literature, we know that if the cone has a small angle, then the limiting pressure becomes degenerate. So PM at time 0 being weakly non-degenerate itself is not enough to guarantee uniform non-degeneracy. So we need something else. And it turned out that we find out one of these two is sufficient to guarantee initial strict expansion. And once you have initial strict expansion, you want to propagate it to all finite time. And then this is the harder part. We need something else. And here I summarize it into two key components. The first one, we call it smaller scale expansion. That is, if you look at T0, time T0, you have the free boundary. And if you compare this free boundary with what happens at time T0 minus tau, suppose the free boundary propagates strictly over the time slot T0 minus tau to T0. So you have you have the free boundary propagates with distance r over this time tau, then the first thing we need is we can have a smaller scale expansion. That is, for all s between 0 and tau, the free boundary at t0 minus s is also away, strictly away from the free boundary at time t0. So we can pass the time scale tau to any number that is smaller than tau. But of course, at the expense of the distance here, the distance between different free boundaries is much smaller. So we can quantify that it is something like s over tau to some power times r. So you can pass one time scale to smaller time scale of strict expansion. And the next ingredient we need is we can show that the strict expansion can be propagated with a fixed time scale. So we have propagation of strict expansion with a fixed time scale, by which I mean the following. So suppose at time t0 and at time 0 and at time t0, we have a strict expansion of the free boundary. And then we want to show that this propagates to t0 to 2t0, and then from 2t0 to 3t0, and so on and so forth. And how we do it is, first, we use smaller scales expansion. So we shrink the ball. So at the expense of shrinking the ball, we can compare not 0 to t0, but sometime t1 to t0. So t1 is closer to t0, and we can say that at this closer time we have strict expansion, that is from smaller scales expansion, and then you use that and you use a lemma. So because between these two times we have strict expansion, so you use the lemma, we know that the average of the pressure in this blue ball is large. Because of this large average, then the free boundary must propagate, the free boundary must strictly expand relatively with respect to streamlines to t0. Okay, so large average here force the free boundary to move. So that by which I mean at time 2t0, the two free boundaries, they are apart. And the reason why I need to shrink the ball and look at smaller time scale is to guarantee that the future time is 2t0. If you do not shrink the ball and apply the lemma directly here, then the time you can propagate will be less than 2t0. And in that case, you will eventually end up with a finite. And we don't want that. We need to propagate the strict expansion property with a fixed time scale. So we need to look at the closer time. So we need to apply this smaller scale expansion first. And then once you achieve that, then you can iterate this argument. You can propagate the strict expansion to a finite time. And then at all these time steps, we know that the free boundary is expanding strictly. And what's nicer is all the estimates are independent of m. So all these estimates are independent of m. And after having the strict expansion with a fixed time scale, then you can perturb the t0 a little bit. You can get a continuous version of this. And then you practice the smaller scale expansion again. We know that the free boundary is strictly expanding at all time scale and for all finite time. So in such a way, we get the strict expansion of the free boundary. And then we know that from this, we know that the pressure variable is weakly non-degenerate near the free boundary for all finite time. And then we can show the convergence of free boundaries in Hausdorff distance. So this is what we have done. And then for the Hausdorff dimension, the estimate of the Hausdorff dimension for the free boundary let me recall the theorem here. So we estimate the Hausdorff dimension of the free boundary. And for this part, we have the true box, and let me first describe the true box, and then let me tell you the proof. Okay. So another result and another proof. So the true box here we have is first we have weak non-degeneracy of the free boundary. So the average of the pressure is not too small near the free boundary. And then we have convergence of free boundaries in Hausdorff distance. And then we have some L1 stability of the solutions. So for the density variables, if you perturb the initial, if you look at the different initial data, then the L1 norm it is under control. The L1 norm of the difference of the density variables is under control. And also the L1 norm is Lipschitz in time, okay? And these two are proved in the incompressible limit literatures under different conditions. And so these two are sort of standard. And the last true is the so-called soup and inf convolution technique. And this technique is widely used in different viscosity solution approach and in various variational problems. If you have any comments or questions, please interrupt me.
Sorry, it was a mistake.
Oh, it's not a mistake. Okay, so so here we will apply this technique, and it is motivated by Kim, Poser, and Woodhouse in their 2019 paper for Hello-Short type equation. Okay, so let me first describe the last technique. So what we do is you look at the density variable rho, and you take supreme of this function over a ball centered at x with radius that is a function of time. And then it turns out that this soup convolution U satisfies some nice properties. For example, Laplacian U becomes larger. Gradient U is equal to gradient of rho, and the time derivative is equal to the time derivative of rho plus r prime times the absolute value of gradient rho. So you can imagine that if r is increasing, then the supreme you are taking over increasing ball, right? So U becomes much larger, and so UT is large, right? When rho prime is positive. So this intuitively this is natural, and with these nice properties, one can show that the rescaling of the soup convolution is a subsolution. So you can choose R to be some nice function, and then this U1 will be a subsolution for a short time. And this is due to the time dependency of the drift and the source. If there's no time dependency, then this can be proved for all times. But because of some time dependency issue, we can only do this for a short time. But that's enough for us. And now let me sketch the proof with all the truths. So we define rho bar as the soup convolution, rho underline as the rho underline as the inf convolution, and we know that rho bar is the rescaling of rho bar is a subsolution, and the rescaling of rho underline is a super solution. Okay, and then what you do is you compare the rescalings of rho bar and rho underline with the solutions with same initial data. And then you have orders of those solutions. And then you use the L1 stability of the solution to show that if rho bar and the rho underlying at the initial time is not too much different, then such small difference will propagate for all time. So here we need L1 stability of solutions. And you can see that we only need sub and super solutions for short time, because once you can prove the inequality for short time, you can iterate this. You can get this for all finite time. And of course, the constants depend on T, but they are independent of M, because the L1 stability is independent of M. And the sub and super solutions and the short time, they are all independent of M. Right, I should have mentioned that this short time here is independent of M. And this turns out to be crucial. So the difference between the L1 difference between rho bar and rho underlying is under control. This estimate is crucial. And I will tell you in a moment. And then what we do is we fix T. We fix T naught, and then I will drop this parameter in the proof. So fix the time and take any R, a small r, take a small radius R, and you cover the free boundary with balls with radius R, and by Vitelli's covering lemma, they are disjoint balls such that 3 times the ball covers the free boundary as well. And then we need to estimate the cardinality of those balls. So we want to show that those balls cannot be too many. And the key idea is to the key idea is to estimate this integral. So we estimate the rho bar over the flattened free boundary. So you look at the free boundary with fixed time, look at one free boundary, and you look at the R neighborhood of it, and we estimate this quantity. And we know this quantity is bounded by above from this estimate, because by the definition, in this flattened neighborhood of the original free boundary, rho underlying is 0. And then because of the stability estimate here, we know that the integral here is under control. Okay, so that's the upper bound. And for the lower bound, we use weak non-degeneracy. So remember, we have the free boundary and we have the flattened one, and the rho bar is the supreme of the solution. Over ball with radius R. And because of the non-degeneracy, we know that if you integrate rho bar near this region, then the integral cannot be too small. In particular, in each one ball, the integral is greater than some constant times R to some power. And if you take, and of course, here we have the density variable. So the power drops down to gamma over m minus 1. And this is a pointwise estimate because rho bar is the supreme. Rho bar is the supreme of everything. And as long as the average is large, then there must be some points that's large. And then you take supreme. And so you get pointwisely largeness of rho bar. And then in one ball, you have that the integral is large, and then you can multiply the cardinality of all the balls. And in this way, we can estimate the upper bound of the balls. And it turns out that this is bounded by a constant that is independent of m times r to the power 1 minus d times r to the power a constant that goes to 0 as m turns to infinity. And in such a way, we estimate the Hausdorff dimension of the porous medium type equations.
Hi, Paul, can I ask you something? So,
Oh, yes, please.
So here it seems like your non-degeneracy estimate is uniform in M, right?
Yes.
So why do you get worse estimate for M, like finite M? I mean, I'm just not following probably.
Oh,
No, you said the Hausdorff. Yeah.
Oh, when M is large, it is actually nicer. When M is large, it is nicer. So all the estimates, weak non-degeneracy, strict propagation, they are all independent of M. And here, so the problem here is Yeah, that's a great point. The problem here is for the continuous equation, near the free boundary, the solution goes down to 0. So, if it is too small, then if it's too small, then this estimate will not tell us the information of the number of balls. So, but if it is non-degenerate, that means it's large. And when you pass to the density variable, the density variable is p to some power m minus 1. That means the density variable is close to the characteristic function. So if it is a characteristic function, then it is it is enough.
Okay.
But now we only have close to characteristic function, and that's why we get some estimates that depends on m, but it becomes nicer and nicer when m tends to infinity.
Thank you.
Thank you for the. Okay. Yes. So this is actually the key reason why we can only obtain Hausdorff dimension that is greater than d minus 1, but asymptotically it becomes a codimensional one geometric object. And then we pass m to infinity, and we can just pass m to infinity in these estimates, and because we know that the free boundaries are convergent in Hausdorff in Hausdorff distance. So you can just basically use the same ball to cover the limiting free boundary when m is large. And in that case, you can pass m to infinity, and you get that the limiting free boundary has finite parameter, or has finite d minus 1 Hausdorff measure. And we're done. Okay, so that's all I want to share with you today, and thank you so much for your attention.
Thank you, Paul, for a great talk.
Thank you.
Are there questions, comments for Paul?
Oh yes, and then oh it's clapped. Sorry.
So while we are waiting for some other questions, can I ask some quick questions? For fixed m or for m large, you estimate the Hausdorff dimensions of the free boundary to be like d minus 1 plus a constant over m minus 1. Is it sharp?
I don't think so.
I mean,
I don't think so, but I don't know.
yeah. I don't know what is that constant gamma star over m minus 1, right? I'm just asking, like whether that sort of order of magnitude of 1 over m is sharp, or you think that it can be better?
Yeah, good question. I think it can be better. It can be much better. This m star, this is from the weak non-degeneracy. So it is a very large constant if the initial, it depends on initial data and so on. So it is a very large constant, but it is independent of m. It only depends on the initial data.
Okay, great. Thank you.
Thank you.
Okay, maybe then let me ask you the second questions while we are waiting. So, and then as you said, I mean, there were some early results by the time group to have some quantitative estimates, right? So for your case, when you try to use, let's say that you have proved the Hausdorff, like the Hausdorff distance of the free boundary, essentially you have the conversion, right? You have it's a Cauchy sequence.
Yes.
Is there any hope to get some quantitative estimates here, or there's still something weird going on?
Yeah, that's a great question. Yes, if I remember correctly, they did. I probably need to check, but if I remember it correctly, I think they obtained a quantitative estimate of the convergence of the density variable.
Yeah.
For the pressure variable converging in space-time L1, if we have the rate of convergence, then we will get some rate of convergence of free boundaries immediately. Yes, you are right.
Okay.
But I think that's something worth thinking about in the future.
Thank you. Are there other questions for Paul? Okay, so if not, then let's thanks Paul again for a great talk, and thank you all for being here for the last talk of this year.
Oh, this year, yes.
Not the academic year, but this year.
Right.
Okay, let me stop.